All right. Hello and welcome to another physics video lecture. Today we're going to be talking about the electromagnetic spectrum. So let's get started. All right. The electromagnetic spectrum. This is a lot of letters, right? It's a lot of word right there. But this concept is something we've seen before, and it doesn't need to be scary. All right. Let's start with the second part of this. What is a spectrum? Okay, if you've never heard the word spectrum before, a spectrum is a range of something, right? From light to dark, or short to tall, or whatever, okay? It's a range of things. The electromagnetic spectrum is a range of electromagnetic waves, okay? Now, we talked about electromagnetic waves when we talked about the types of waves. And what an electromagnetic wave is it is a wave that is both an electric field and a magnetic field at the same time, which is kind of nuts. But we'll delve into what this really means and how this is affected. But if you look at right here, you can see how they're set up. The electric field and the magnetic field are 90 degrees to each other. And what that means is if the electric field is vibrating up and down, the magnetic field is vibrating side to side. So they're vibrating, if I can do this, like this the entire time. They're 90 degrees to each other. And we'll talk about this more when we talk about magnetism. But what you need to know is that the most important part, and what we mentioned last time, is that electromagnetic waves, or EM waves, okay, do not need a medium to travel through. Now remember, mechanical waves, like ocean waves or sound waves, they need atoms in order to vibrate them, right? I say this all the time. If you take the water out of the ocean, you don't have any more ocean waves, right? In space, no one can hear you scream because there's no atoms to move. There's no medium to move, right? Well, electromagnetic waves are special because they can travel through nothing. In fact, that's where they move the fastest. So these electromagnetic waves, they're their own energy, which is really cool, okay? So here is the first picture of the electromagnetic spectrum. We're going to break it down. We're going to look at all of these different parts. A big thing to remember here is that all of these electromagnetic waves, they're all the same thing, okay? The only thing that's different about them are their frequencies, okay? So let's just jump here for a second. I ask you, how fast does light travel? Okay, and hopefully you can at least guess that all light travels at something called the speed of light, and that's very good. Now, the first thing we need to understand is that all electromagnetic waves travel at the same speed whenever they're in a vacuum, okay? And if you remember, a vacuum is when there's nothing, okay? Remember the bell in the bell jar? You use a vacuum pump, you suck out all the air. That's what creates a vacuum. A vacuum is nothing. It's empty space. That's why we call space space. Now, all electromagnetic waves are light. I will use those words interchangeably. Light is an electromagnetic wave. Electromagnetic waves are light. Cool? The speed of light, okay, which we use the letter little c for, okay, is 3 times 10 to the 8 meters per second. Right, I should have put the little meters per second over here. I hope that's not confusing, but this is the speed of light. If you wanted to convert this into miles per hour, it'd be about 670 million miles per hour. 3 times 10 to the 8 is 3 with 8 zeros after it, which is 300 million meters per second. So light travels 300 million of these in 1 second. It's the fastest speed in the entire universe. It's kind of like the speed limit of the universe. Nothing can travel faster than this, which is pretty cool. Again, light travels the fastest in space because space is a vacuum. Light travels the fastest when there are no atoms in its way, all right? When light goes from space into a medium, it actually slows down. As soon as you start putting atoms in light's way, it slows down, which is the opposite of mechanical waves. In mechanical waves, the more atoms you have, the faster they go. Sound travels the fastest in a solid. This is the opposite, okay? As you can see here, light travels 300 million meters per second. In a vacuum, it travels just a hair slower, but not detectably slower in air. But once it goes into water, it goes down to 225 million meters per second. That's substantial. Okay, that's like 20% slower, right? 25% slower. When you go into a solid like glass, it goes down to less than 200,000 meters per million meters per second, which is now we're at a third less than it was in the vacuum. And when you go into a solid, it goes all the way down to about 125 million meters per second. So again, fastest in a vacuum, second air, then water, glass, and it's actually going to go slowest in a diamond. Why? Because the diamond is the hardest element, or the hardest mineral that we have, and so light goes the slowest in it. Similarly, sound travels the fastest in a diamond. Isn't that cool? All right, so let's talk about this spectrum. Now, the first part of the spectrum I want to talk about is what we call visible light, because when you think of light, this is what you think of. And whenever you talk about light, you may remember these letters. Roy, G, Biv, R-O-Y, B, G, B, I-V, okay? What do these stand for? You know this. Red, orange, yellow, green, blue, indigo, violet. These are the colors of the rainbow. And the reason that you remember Mr. Roy G. Biv's name, okay, is because this is the order that they appear in, okay? This is the order that they go in the spectrum. And they are organized by their frequencies and by their wavelengths. So this is something that is super important, okay? Now, visible light is not the only type of light, which is kind of crazy, but it is true, all right? We actually have 7 types of electromagnetic waves, okay? We have radio waves, microwaves, infrared waves, visible light, ultraviolet waves, X-rays, and gamma rays, okay? When we're talking about these, you need to understand that all of these electromagnetic waves are the same thing. They're all an electric field and a magnetic field vibrating together. They all travel at the same speed when they're traveling through space. And most importantly, none of them need a medium to travel through. The only thing that's different about any of them is their wavelength, okay? So that's why we call it a spectrum. The spectrum goes from radio waves over here, and radio waves have the longest wavelengths, okay? Which means they have the lowest frequency, all the way up to gamma rays, which have super tiny wavelengths, which means that they have the highest frequency. This is the electromagnetic spectrum. And this is a great video from NASA about it. So if you want to watch that, highly recommend it. Now, I've included a few other versions of the spectrum, okay? Again, here, this one's a little crowded, but you can see that we start all the way over here, okay, with the low frequency radio waves going through microwaves, infrared, your visible light rainbow, to ultraviolet, X-rays, and gamma rays. And again, we start with long wavelengths over here, and we go to really short wavelengths over here. Oh, what's this? You want another one? All right, here's another one. How about this one? Again, same thing. Long wavelengths on this side, short wavelengths on this side. And that is what is different between all of these, okay? So again, if anybody ever asks you what's the difference between the color red and the color yellow, the answer is red has a longer wavelength and a lower frequency, whereas yellow has a slightly shorter wavelength and a slightly higher frequency. You with me? Good. Okay, so how can you remember this? These are the letters that you got to remember. R, M, I, V, U, X, G. Radio waves, microwaves, infrared waves, visible light, ultraviolet, X-rays, and gamma rays. Okay? What I suggest is that you remember a mnemonic in order to remember these. Okay? A mnemonic is just a sentence where each letter of the sentence starts with one of these. You know these things. Please excuse my dear Aunt Sally, etc., right? Here's one. Raging Martians invaded Venus using X-ray guns. Pretty good. Makes sense. You can remember that, all right? And it gives you all of the letters in order. One that we came up with as a class a few years ago is, really, man, I'm very upset with my ex-girlfriend. Now, this one has the with my in it, which can throw you off, but none of these start with a W or an M, so it's not a huge deal. Come up with your own. Email it to me. Let me know. I'll put it on the chart. But all of these are very, very, very useful in remembering the order of the spectrum. Let's go through each one of these, starting with the longest wavelength and the lowest frequency. Starting off with radio waves. Now, you know what a radio wave is. We use these for lots of things. Probably most notably for the radio, okay? This is exactly what you're thinking about. Radio waves are the waves that we send about to get radio signals, okay? But we use radio signals for lots of things. We use it for TV remotes. We use it for our cell phones, use a ton of radio waves. In fact, that's mostly what they use. Any kind of wireless device, Bluetooth, any of that stuff, all of those things are radio waves, which again is light. It's a form of light. Now, we can't see it, but there are radio telescopes that can. Radio waves can be huge. They can be the size of buildings. They can be miles long, right? So you can have a mile-long wave. And this is why it's cool to use them for communication, right? Right now, coming out of this room, I'm recording this on my cell phone. My cell phone is getting zapped with radio waves left, right, and center. It's how it picks up my emails or my text messages. It's how, radio stations are broadcasted. So there's radio waves flying around you all the time. And because their wavelength is so long and their frequency is so low, they're not dangerous, at all. They're everywhere, okay? Again, they're any wavelength bigger than 1 millimeter. So any wave that's bigger than a millimeter, okay? So again, you go from a millimeter to like a mile long. Those are all radio waves. And their frequency is gonna be 3 times 10 to the 11 hertz. So notice as we move forward, the wavelengths are gonna be getting shorter and the frequencies are gonna be getting higher, right? As the wavelengths get shorter, the frequencies get higher. And again, like I told you with sound waves, the frequency of a sound wave determines its pitch. Well, the frequency of an electromagnetic wave determines literally what it does and how much energy it has, okay? So just to remember this, the higher a frequency, the higher the energy that wave has. Higher frequency equals higher energy. Cool? All right. Next we have microwaves, okay? You probably have a microwave, right? And microwaves are exactly that. We use them for microwave ovens, but we use microwaves for lots of things. We use them for radar, we use them for communication satellites. In fact, your cell phone also uses microwaves along with radio waves to communicate, right? So again, microwaves. Radar detector guns use microwaves. So do radar detector gun detectors and so on and so on. And so do communication satellites. Again, the wavelength here is starting to get a little bit smaller. Anything that starts off at 0.001 meter all the way down. I should have flipped these numbers here. I might do that. But anyways, all the way from this tiny, tiny, tiny number right here, 2.5 times 10 to the negative fifth to 1 millimeter. Now we're starting to get seriously small, like smaller than you can see with the naked eye. And notice now our frequencies are going up. We went from 10 to the 11th to 10 to the 13th, okay? Do you need to remember these numbers? No. You do need to remember that radio waves have longer wavelengths and lower frequencies than anything else, right? Next, we have infrared waves, okay? An infrared wave is the wave that is just below red on the spectrum, so it's easy to remember. Infra means below, and infrared waves are heat, all right? We detect them as heat, and this is what you see if you've ever seen night vision goggles, or if you have like a heat lamp, if you've ever worked in a restaurant or you have one in your house to keep food warm, any kind of heating lamp, that is an infrared wave. The reason that we have life on this planet is because we get infrared radiation from the sun. That is what warms up our planet, all right? Notice again, our wavelengths are now getting smaller. Okay? Again, I should have flipped these. Not consistent, Mr. Norris. And our frequencies are getting bigger from 10 to the 13th to 10 to the 14th hertz. So if you've ever seen Predator or seen night vision goggles, these colors right here, those are the infrared radiation. So we can see these if we use the right technology. The red areas are the hottest and the blue areas are the coldest here. infrared is heat, right? Now next up, we have visible light, right? So after infrared, we literally have red, orange, yellow, green, blue, indigo, violet. Here's your Roy G. Biv right here, okay? Now, visible light is special to us because it is the only part of the spectrum that we can see. These are the only electromagnetic waves we can see, right? Their wavelengths are very specific, 7.5 times 10 to the negative 7th to 4.0 times 10 to the negative 7th meters. So it's a very, very, very small section of this. These waves are only a couple 100 nanometers in difference, right? It's the only part of it we can see. Interestingly enough, there are animals that can see other parts of the electromagnetic spectrum. That's super cool. And again, notice again, our frequencies, we're going from 10 to the 14th to 10 to the 15 hertz. So our frequencies are going higher and higher as our wavelengths are getting smaller and smaller, okay? And that's really everything about visible light, right? It's the part that we can see. And we see that red has, again, the longest wavelength and the lowest frequency, and violet has the shortest wavelength and the highest frequency, okay? As our wavelengths get smaller, okay, and our frequencies get higher, after violet, we're gonna go above violet, and again, above is ultra. So literally ultraviolet. These are the rays that are above violet. They're the rays that have a higher frequency than violet, okay? You may know UV rays because this is why you wear sunscreen. UV rays are the rays that come out of the sun that cause sunburns and skin cancer. They're nasty, okay? Now this is a really interesting point to start here. Once we get past visible light, okay, visible light, infrared, microwaves, radio waves, especially microwaves and radio waves, in normal doses, these things are not dangerous at all. A lot of people think microwaves are this dangerous form of radiation. They are a form of radiation, but so is light. Okay, the light you see off the mirror is a form of radiation. Microwaves can burn you in high doses. I think technically radio waves can too, but on normal levels, like the kind that come out of your microwave at home, they're not dangerous. The way the microwaves work is actually interesting. Remember we talked about natural frequencies and resonance? Microwaves can have the same frequency as water. And what they do is they literally vibrate the water inside of the food that you're heating up so much that the water turns to steam and it heats your food back up, which is why when you zap bread in a microwave, it tastes real gross because you've actually taken all of the moisture out of that bread and made it really like hard and just gross. So try not to microwave bread. Radio waves, microwaves, not dangerous. Infrared waves obviously can be dangerous if there's enough of them. Heat can burn you, but in normal doses, it's something that you need. We need heat in order to keep things growing and to keep the planet from freezing, right? Visible light, obviously not dangerous, right? It's what we use to see, okay? But once we get past visible light, ultraviolet light is now in an area where its frequency is high enough and its wavelength is short enough that it can start messing with our actual cells, okay? And this is what causes that sunburn. That frequency is so high and those wavelengths are so small, it can actually start penetrating our cells and messing with it, which is not good, okay? Again, wavelengths are getting smaller, frequencies are getting higher. Ultraviolet comes from the sun, along with the infrared heat and the visible light that lets us see. Now, when we get a step shorter, okay, wavelengths get shorter, frequencies get higher. Now we have X-rays. You know what an X-ray is. We use them for medical imaging. We also use them in astronomy, okay? We use them, we look for X-rays coming from other galaxies and other planets, okay? X-rays can be dangerous. If you just X-ray your arm or your leg, it's not dangerous. If you do X-ray your vital organs, you tend to wear a sheet over your vital organs. There's like lead sheets that are used. Obviously medical professionals and radiologists are super careful, but X-rays can be dangerous. Okay, this is why we don't X-ray babies. This is why we use ultrasounds, remember? Okay. And again, we use X-rays for all sorts of cool things, okay? And last but not least, the smallest wavelength and the highest frequency goes to our best buddy, gamma rays, okay? Gamma rays have the highest frequency, which means they have the highest energy, okay? Funny enough, we use gamma rays to kill cancer cells. They are so tiny and have so much energy that we can use them to pinpoint and zap cancer cells and kill them. Also interesting is that if you're exposed to a bunch of gamma radiation, it causes cancer. So ironically, gamma rays can both cause cancer if you're exposed to a lot of it, or if you're exposed to little tiny pinpoints of it, you can use it to actually kill cancer cells. Interesting, right? We see these a lot coming from celestial bodies, stars, things like that, because they're super high energy. They are the things that reportedly made the Hulk in the Marvel universe. Don't zap yourself with gamma radiation because, right, not good for you. But they have the tiniest wavelengths and the highest frequencies. So they're the most dangerous of all of them, all right? Now, when we're talking about these waves, we know their speed in a vacuum and in air. We know that they do not need a medium to travel, and we know that the only difference between all of these electromagnetic waves is their frequency, right? So we can use the same wave equations that we've been using. So if you want to find the frequency or the period, use the exact same equations, right? Frequency is cycles per second. Period is how many seconds it takes to complete one cycle. And you can find them you can find the frequency by dividing 1 by the period, or you can find the period by dividing 1 by the frequency. So same equations as before, same here. The velocity equation still exists. Velocity equals frequency in hertz times the wavelength. So if you multiply the frequency by the wavelength of any wave, you get its velocity. Now here's the fun thing, because these are all light, their velocity is always going to be the speed of light, 3 times 10 to the 8th, which is on your equation sheet. It's a number you always have. So let's take a second and let's look at 2 examples real fast. Okay, the color violet, right, which has the highest energy and the highest frequency, has a period of 1.33 times 10 to the negative 15th seconds. I forgot to put seconds right there. Let me add that. I'll change that before I give it to you. What's its frequency? Now, this is easy. Frequency is equal to cycles per second, or 1 divided by the period, okay? So if I just fill in this number, I know that the frequency is 1 divided by 1.33 times 10 to the 15th seconds, which I meant to put in there, because we measure periods in seconds, because it's the amount of time to complete one cycle. So one of these cycles takes an insanely short amount of time to be completed. Well, it's 0.140133 seconds. All we got to do is put this into our calculator, which over here. Here we go. So I'd go over here and I go 1 divided by, and then I do parentheses, 1.33 times 10, a to the b, 15. I go forward and close my parentheses, and that gives me my answer, which is 7.5 times 10 to the negative 16th. Right? Very cool. Okay? So my frequency here is equal to 7.5 times 10 to the 16th hertz. Negative 16. Very important. So this frequency is insanely small. Rough. I'm sorry. Negative 16. Yes. Very good. Okay. Oh, I did this backwards. I was about to say, that number looks wrong. Mr. Norris, you said 15 when you meant negative 15, didn't you? And I would say, good job. I did mean negative 15. Sometimes I make mistakes. So our real answer, there you go. I was about to say, that number doesn't look right. Is 7.5 times 10 to the 14th hertz. Exactly. I was about to say, why is the frequency so small? We have a very high frequency. 1 divided by the period gives us our frequency. So now we can use this frequency and we can figure out what the wavelength is, all right? So look right here. Now we know our frequency is equal to 7.5 times 10 to the 14th hertz. Let's find our wavelength. So here's what we know. We know our frequency is equal to 7.5 times 10 to the 14th hertz. I can write that nicer than that, can't I? We know that the speed of light, our velocity, is always 3 times 10 to the 8th meters per second. And we are looking for our wavelength. Okay. So we know that our equation here is going to be velocity equals our frequency times our wavelength. So now we just have to fill in these rather large numbers, but nothing difficult. 3 times 10 to the 8th equals our frequency, which is 7.5 times 10 to the 14th times our wavelength. Now again, we have seen this before, and even though these numbers are large, we're doing the same thing. We want to get the wavelength by itself. So we got to move this number right here. We got to move the frequency. So this is multiplication, so we just do the opposite. And we divide. 7.5 times 10 to the 14th. Whatever we do to this side, we do to this side. Anything divided by itself is 1. And this right here is something I'm going to put in my calculator. So I go back to the old Kakalaki. Yay! Clear it. Now I'm going to go parentheses. 3 times 10, a to the b, 8, forward, close parentheses, divided by, parentheses, now put this in, 7.5 times 10, a to the b, 14, forward, parentheses. And I get this, 4 times 10 to the negative 7. Actually the actual wavelength of the color violet, which is cool. If you are unaware of the color violet, it is pretty much purple. Is it exactly purple? There's debate there. 4 times 10 to the negative 7 meters, which can also be written as 400 nanometers. Okay, it's the same thing. But this is the actual wavelength of this color right here. And again, a little smushed, but as you can see, it's the same thing. It's a 3-variable equation, and if it's being multiplied in the equation, you want to move something, you divide it. Same as before. Now, the last thing is I want to show you how I fill this out. So if I were to have a test, here is how I would remember the electromagnetic spectrum. I'm going to write all of this in purple just so it's a little easier to see. All right. The first thing you got to realize is you always start with Roy G. Biv. First thing you do, right? Red, orange, yellow, green, blue, indigo, and violet. Now, you guys would assume learned this probably in grade school along the way some way, right? But Roy G. Biv is a classic, right? One of the best mnemonics ever. Start here. So if you get a test and you have to remember the electromagnetic spectrum, start with Roy G. Biv, just write it down. Okay? And everything else kind of falls into place. Let me show you what I mean. Here we have red. Red is right here. We know that one of the waves is infrared. So infrared means less than red. So where does infrared go? Goes next to red. Goes right here. So I'm going to write that down. Yay. And we know another wave is ultraviolet, which means it is above violet. So ultraviolet goes right next to violet. Oh, if I didn't mention, you may know ultraviolet as UV radiation. It's the same thing. Okay, we are like a third of the way there. Almost half, actually. So, the next two easy things to remember are the most dangerous and least dangerous. If you remember, okay, gamma rays made the Hulk. They can cause cancer. They're the strongest. So gamma radiation goes all the way here on the dangerous side with the high frequencies, okay? And all the way here on the not dangerous side we have our radio waves. Radio waves are the least dangerous, right? You can start with radio and gamma, if that makes it easy. Just remember, radio waves, they have these super long waves. They're in your pocket right now. They're coming out of your cell phone. They're not dangerous. That's why they got the big wavelengths. These little short wavelengths, gamma rays, really dangerous. They belong over here with UV rays, okay? They're dangerous. Now there's only 2 spots left, and this is what you gotta remember. You just gotta remember that X-rays belong on the dangerous side, and microwaves belong on the not dangerous side. And voila, you have the entire electromagnetic spectrum mapped out. If you want to finish these other questions over here, let's look at the wavelengths. Over here, on this side, on the left side, we have these long wavelengths. So remember that these are long. I recommend drawing this wave like this when you get this, where you go like this, and then you go, and you get really small over here. I'm bad at drawing. So remember, you have long wavelengths on this side and short ones on this side. That's a terrible wave, I know. But this is what I was trying to draw. Here you have long wavelengths, which means over here, you have short wavelengths. And you just gotta remember, wavelength and frequency are inversely proportional, which means over here, you got low frequencies, low energy. And over here, you got high frequencies, high energy. And that's it. That's the electromagnetic spectrum for you, all right? All right, guys, hopefully that was helpful. Again, watch the video, take down the notes, and use this to complete your DOL. Email me or find me during tutoring on Zoom with any questions. Have a great day.